Okay, before we get on to the lesson, a few things. Again, reminder, next week on Friday, electricity quiz. And I'm gonna make another important announcement about that. It's gonna be set up the same way you did the biology quiz. It's gonna be online, it's gonna be on your Chromebook. And again, I think I know now who does not have access to their Chromebook, so I don't think that has changed, but let me know if it has. I am going to make a change though in terms of how this is going to be done. You can use your notes. Why not, right? You'll understand why, because there's a lot of things that we're applying. So you just having that knowledge there and being able to apply it. Now, so if you've been printing up your notes, if you've been jotting notes down or copying them from your Chromebook to your notebook, great. I do know though that some people may not have access to a printer, and because you're going to be using your device, your Chromebook, as you write the quiz, that is not going to allow you to just quickly refer to your notes. That's going to be a bit of a problem if you don't print them out or haven't copied them out. So if you're totally stuck, just create a cheat sheet. I don't expect you to write down every single thing from the note. I'm hoping that some of that stuff that you have from the notes kind of makes sense, so you don't necessarily have to write down something you already know, but just the sticky parts, the parts that you're going to forget. Like if it's the equation, if it's Ohm's law, if it's you trying to remember the units that apply to, current, the fact that I represents current, go for it. If you're not quite sure or you think you're going to forget some of those concepts around static electricity, jot those down. So I encourage you, you're allowed to have your notes with you for this quiz. And what's the plan moving forward? So today we're talking about power. Monday we're going to talk about power generation, and then I'm stopping there. Wednesday next week is going to be just for review and give you guys a chance to sort of catch your breath a little bit, review, and if you need to prepare your notes or whatever. And then Friday we're writing the quiz. That's the plan moving forward. All right. So this weekend, if you have any questions, send them my way, and I'll try to get back to you ASAP. All right. Let's get on with the lesson. Today's topic is about power, and power is defined as the rate in which electrical energy in a circuit is converted into other forms of energy. And that is really what we've been doing for the last 2 weeks now, using electrical circuits. We've been taking batteries and attaching loads to it and creating from electrical energy either light or creating a motor that will spin or turn. That is really what circuits do, and we can calculate the power in a circuit using a formula, and that is what we'll be focusing on today. Power can be calculated using the formula power equals current times voltage. Current and voltage, two terms, two concepts that we've been looking at in the last week. Now, power is measured in a different unit called watts. And you might recognize this if you've ever dealt with light bulbs and you're looking at light bulbs and trying to determine, how much energy they use. You might look at something like watts or the power rating of it. Is it a 40 watt light bulb? Is it a 60 watt? Same thing with any electrical device for that matter. Chargers for your phones or your tablets. I know for Apple, they will often classify their different chargers. The ones that are the small sort of wall chargers for your phone, those are like 5 watt chargers. The larger ones for like an iPad are 12 or 15 watt. And then it gets higher from that if you have like a computer. They could have like a 32 watt charger. So we use watts as a way to describe the amount of electrical energy that circuit or device will use up, because essentially it's that power that gets converted into other forms of energy. Now, when it comes to watts, and this will actually apply to the other units we've been looking at too, if it's amps or volts or ohms, but we especially see it in watts because it can get quite large, the power ratings that we're looking at. If you're talking about an oven, or if you're looking at the power consumption across a city, the numbers can get quite large. And as a result, there are ways that we can express large amounts of watts using prefixes on that unit, such as kilo or mega or giga. So you could have a kilowatt, you could have a megawatt, you could have a gigawatt. What do those mean? That's what we're going to talk about next. So we measure power using a unit called watts. However, like I said before, this unit can quickly scale up, or these values can scale up. So we need to have a way of being able to describe really large values of power. So yes, we can measure power in watts. However, we can also describe power, large amounts of power, in kilowatts. And what a kilowatt is basically 1,000 watts. So if I say we have a 2 kilowatt power source, that means that it's a 2,000 watts that are coming out of that power source. All right? It goes up even more. We have what we call a megawatt. And what that means is 1 megawatt equals 1 million watts. So a 5 megawatt usage of power is the same as me saying 5 million watts. That's like a 1 followed by like 6 zeros. Finally, we can say 1 gigawatt. And 1 gigawatt is the same as me saying 1 billion watts. That's like 1 followed by 9 zeros. That's a huge amount of power. So I just want to be just make sure that you're aware of this, because you might see power being expressed in kilowatts. And if I say that we have 3 kilowatts of power here, that means it's 3,000 watts. Now, I know it can be intimidating when we start thinking about, well, there's watts, and then there's kilowatts, megawatts, gigawatts. How do I keep this straight? I'm hoping that you can draw parallels to things that you already know, because those prefixes, mega, kilo, giga, you've used those things before, and those relationships will apply and hopefully help you make sense of those prefixes. For example, distance. One classic unit of distance is meters. We measure things in meters. However, we can measure long distances. For example, if we were to say it's 200,000 meters from London, Ontario to Toronto, Ontario, that's a lot of meters. However, we often will express it in kilometers. Instead of us saying 200,000 meters to Toronto, we will say 200 kilometers to Toronto. Is there an actual difference between these two values? Yes, there is. I know it's horrifying, but yes, there is a big difference between this lowercase m and this uppercase m. Here we go. The big M, the one we just talked about, stands for mega, and that means 1 million of something. All right? The little m stands for milli, and it stands for 1/1000th of something. So going back to our meter stick example, we can call, a meter stick 1 meter. However, we have other lines on that stick as well, like centimeters, and then even smaller lines that represent millimeters. That's what we're talking about here. 1 millimeter, that little small tiny marking there on your meter stick, represents 1/1000th of a meter. Not to scare you enough, but I just want to make sure you understand there's a big difference between the small m and the big M. Back to this. Again, this is what we were just talking about. 1 watt, 1 kilowatt, 1 megawatt, and 1 gigawatt. Where does the milliwatt stand in this? Well, it would be here. Because again, we're saying it's 1/1000th of a watt. So in order to make 1 watt, you would need 1,000 milliwatts to give you 1 watt. If you wanted 1 kilowatt, you would need 1,000 watts to give you 1 kilowatt. If you wanted a megawatt, you would need 1 million watts to give you a megawatt. If you wanted a gigawatt, you would need 1 billion watts to give you a gigawatt. I hope that makes sense. So again, the reason why I'm going through this is so you are able to recognize when you start seeing values measured in megawatts or gigawatts or kilovolts or milliamps. They are the same values we were looking at before. Like amps is a measurement of current, volts is a measurement of voltage, watts is a measurement of power. But if you start seeing those little prefixes like milli or mega or kilo or giga, I want you to understand what those mean.
The flux capacitor stores. This sucker's electrical. But I need a nuclear reaction to generate the 1.21 gigawatts of electricity.
1.21 gigawatts! 1.21 gigawatts! Great Scott! What the hell is a gigawatt?
because it's important. You will see that out there in the real world. All right, so we've got the unit thing sort of covered, hopefully. And what we're going to do next is get back into that equation. Power equals current times voltage. How can we use this, and how can we solve some basic problems with this formula?
All right, so how could you use this formula to try to solve for different values, whether it's power, current, or voltage? Let's do a couple of examples here, but before we do that, let's take a look and review just to make sure we understand here. Power is going to be measured in watts, all right? To make this equation work, we got to make sure that the values going in there for power are in watts, and that current, which is represented by I in this formula here and here, that is going to be measured in amps. Voltage needs to be measured, obviously, in volts. There we go. And you saw this already. We're going to make use of this triangle here because, again, this is going to allow us to manipulate this formula to solve for different values. So let's go to our first example here. What is the power of a light bulb if 0.5 amps passes through it while connected to a 120 volt outlet? And again, I guess the biggest challenge here is trying to figure out what we're trying to find here. And usually it's revealed to you in sort of this format. What is the power? Bang. That's what we got to find. What is it? Well, let's do what we got to do. We got to cover up the P, and now we're left with I and V on the same line, side by side. That means that we multiply those two values together. That means our equation that we're going to use is going to be this. Power equals current times voltage. And then we next plug in these values here. Again, current is represented by I. Then we measure current in amps and voltage in volts. So we just plug in those values like that. And then we complete the calculation. And we end up getting that. Now again, cannot stress enough, please make sure you don't just give me the 60. Make sure you include there the actual units there in watts. That's our first example. Let's try the next one. How many amps goes through a 50 watt toaster if it is connected to a 120 volt outlet? And again, what are we trying to find here? Which part of this triangle do we need to cover up? Well, let's take a look. How many amps? Bam! Amps. Now, you got to be clever here because I'm not specifically saying how much current. You got to understand that amps is a measurement of current, so therefore we got to be looking for current. Now again, second challenge is where the heck is current in this? I don't see a C. Well, you won't, because current again is represented by I. So there it is. Cover up the I, and now you have these two values, power and voltage. Now because there are sort of ones on top of the other, that is the actual formula. Power divided by voltage. And we should write the equation like this. Now, once we've got that, let's plug in the values. Now, don't forget, make sure you're aware of power is measured in watts, voltage is measured in volts, so that must mean that the values going in must be 50 watts on top divided by the 120 volts below, and complete the calculation. 50 divided by 120 gives you 0.416666 repeating. What the heck? Well, we got to round this off, and I will just say let's round it off to the second decimal place, so it becomes 0.42, and don't forget your units. Again, this is a measurement of current, I there, and we measure current in amps, so there it is. Whew. All right, folks, those are the two examples there, and again, a third example that I would have thrown at you is we would have been solving for, let's say, V instead, and we'd cover up the V, and it would be power divided by current instead. But you get the idea. Don't forget your units. Please make sure you're using the proper units and including in the units there at the end, and make sure that you're using the proper form of that equation. All right? Good luck.
So connecting this to a real world application, and hopefully you have a better understanding about what these numbers mean, let's take a look at a really common example. If you've ever gone shopping or looked at light bulbs, this is a great way to sort of illustrate your new understanding about power.
Because we will often describe light bulbs based on the watts that they use. Now, we have 3 light bulbs here. All 3 of these light bulbs are equally bright. So whether you're using the one on the left or the one in the middle or the one here on the right, if you turn them on, they will release the same amount of light. All right, Next, I'm going to show you the wattage of these light bulbs, or the power rating of these light bulbs. The first one there on the left is a 40 watt incandescent bulb. This one here is a 15 watt CFL, and this one over here is a 7 watt LED. If I were to ask you which one is the most efficient or power efficient, you would know exactly what that was. Well, I hope so. The LED is the most power efficient. And the reason why is because of this number here. But you now have an understanding of where this number comes from. This number, one way to calculate it would be current times voltage. And if we end up with a lower number overall, that must mean that the current and voltage are also smaller as well, because power is current times voltage. So if I've got a small power here, the current and voltage must also be fairly low as well, compared to, say, something like the 40 watt light bulb over here on the left hand side. That is a much larger power rating for this bulb. That's a 40 watt. And as a result, you know that the amount of current and voltage combined is larger than, say, this LED bulb here on the right hand side. So we're trying to make these connections back to what we see out there in the real world. And we're now starting to see and understand what goes in to these numbers here: the 15 watt, the 7 watt, the 40 watt, the 100 watt light bulb, your 28 watt charger for your laptop. You now have a better understanding, I hope, that's the goal here, to understand what is behind those numbers.
So another example where you will come across terms like wattage or power or volts, current, amps, that kind of stuff. TV and movies. You will see a lot of references to those terms. And I'm going to show you a clip here from Apollo 13, one of my all-time favorites. And if you have not seen it, you should see it. It's actually really, really good. And it's the scene where the astronauts are now officially in trouble. They are sort of stranded out in space, and they are trying to figure out a way of getting these astronauts back to Earth. The thing is that they begin to realize there's only a certain amount of power left on the capsule. So here is a clip. Let's see if you can catch the terms that they're trying to use in this scene that relate to electricity and what we've been talking about in this unit. Let's roll the clip.
That brings them to about there. Gentlemen, that's not acceptable.
Gene, we gotta talk about power here. Whoa, guys! Power is everything. Power is everything.
What do you mean?
Actually, hi. Power is actually current times voltage. Actually.
Without it, they don't talk to us, they don't correct their trajectory, they don't turn the heat shield around. We gotta turn everything off. Now. They're not gonna make it to re-entry.
What do you mean, everything?
With everything on, the LEM draws 60 amps.
And amps is a measurement of current.
At that rate, in 16 hours, the batteries are dead, not 45.
And if we're talking about batteries, that's direct current, right?
And so's the crew. We gotta get them down to 12 amps.
How many?
You can't run a vacuum cleaner on 12 amps, John.
Actually, 12 amps is enough to run a vacuum cleaner.
You gotta turn off.
It's just more efficient now.
We have to turn off the radars, cabin heater, instrument displays, the guidance computer, the whole smack.
Whoa, guidance computer. What if they need to do another burn? Gene, they won't even know which way they're pointed.
The more time we talk down here, the more juice they waste up there. I've been looking at the data for the past hour.
That's the deal?
That's the deal.
Okay, John. Minute we finish the burn, we'll power down the LEM.
All right.
Now, in the meantime, we're gonna have a frozen command module up there. In a couple days, we're gonna have to power it up using nothing but the re-entry batteries.
We've been tried before. Hell, we've never even simulated it before, Gene.
Well, we're gonna have to figure it out. I want people in our simulators, working re-entry scenarios. I want you guys to find every engineer who designed every switch, every circuit, every transistor, and every light bulb that's up there. Then I want you to talk to the guy in the assembly line who actually built the thing.
Light bulbs and transistors, they're just loads. Okay, I'm gonna go.
Find out how to squeeze every amp out of both of these damn machines. I want this mark all the way back to Earth with time to spare. We never lost an American in space. We're sure as hell not going to lose one on my watch. Failure is not an option.
Whew. That was tense in there, hey? All right. Well, I'm glad we're out of there. So look, that's the end of the lesson. What are we now going to do? I'm posting up some simple practice questions again for power to see if you can manipulate that equation, solve for those values, and use that triangle. Again, I'll be posting up the answers later on, and hopefully you all have no problems with it. But if you do, let me know. Let me know. It's not a big deal. Send me a question, email, or in the comments, and I'll try to get to you ASAP. That's it. End of the lesson. I wanted to end off on that clip. Space, I'm hoping you're able to catch some of those terms. And to illustrate the fact that these concepts that we've been looking at in our unit on electricity, they are in use around us all the time. You go to a store, you start getting into stuff like your electronics, you are going to start to see terms like voltage, current, resistance, and now power. So there it is. End of the lesson. The more you know.